For this next video here, we're going to get into the fourth quantum number that we didn't talk about in the last chapter, m sub s, and its relation to the concept electron spin. So the reason we're going to start worrying about this is we're going to now be looking at multiple electron atoms. So we're going to see how this is going to come up and how the final quantum number relates to this. So m sub s is the spin quantum number and represents the spin of the electron. For the purpose of this class, just understand that spin is a fundamental property of all electrons. We're not going to worry about technically what does that mean, because in the classical sense, we can't really think of it the same way as we might think of, like if we had a negative charge and it was spinning, you'll learn in physics that should create a magnetic field. But we know that electrons that go around the nucleus don't do that. So for now, for this class, just going to say spin is a property of the electrons. It's something they do, and we're not going to go into it beyond that. Unlike the other quantum numbers, which had varied a lot of different possible values depending on other ones, m sub s only has two possible values ever, +1/2 and -1/2. There's nothing else it can be. There are no other exceptions, like when n is exactly 1, it can be something else. It can always have two possible values, and there are no other values it can contain. The way we draw it, it looks like this. So this is the example of a hydrogen atom. And so what we do is we draw our orbital box, which is going to represent our orbital. So in hydrogen, we have our first electron, this 1s. If we remember from last chapter, we talked about some. That means that n is going to be 1, L is going to be 0, and because of that, m sub L is also going to be 0. Now, when we want to draw the electrons, we're going to actually put them inside a box that matches the label for their orbital. So because of these particular values relate to the 1s orbital, we'll put it in a box that we label 1s. And when we do it, we're going to have to draw an arrow. Now when you notice, something about this arrow is that this arrow is pointing up. And it has a half arrow. That half up arrow is related to it having an m sub s of +1/2. If it were a half down arrow, that would mean m sub s was -1/2. That's how we represent these two different electron spins. And as you might imagine, if you had an atom that had two electrons in it, and one was +1/2 and one was -1/2, we would draw 1/2 up and 1/2 down. And they would act as a pair that come together. So yeah, when two electrons in the same orbital, they have to be paired, where one is spin up and one is spin down. You will never see two spin up electrons in the same orbital. You will never see two spin down electrons in the same orbital. So if you were to try to draw this, for example, and draw two of them up, that would be incorrect. You have to have one up and one down. This property is related to something we call the Pauli exclusion principle, of why you only see one up and one down instead of just two up. So what the Pauli exclusion principle states is that no two electrons in an atom can have the same set of 4 quantum numbers. For example, in a helium atom that has 2 electrons, and we describe them by the following quantum numbers. In helium, one of the electrons has an n equal to 1, an L equal to 0, an m sub L equal to 0, and an m sub s of +1/2. The second electron, the first 3 quantum numbers don't change. It's still in the 1s orbital, but now m sub s is -1/2 in that case. So next what we want to do is we want to look at, so what would that look like as an orbital box diagram? So helium, both of its electrons occur in the 1s orbital. So it only needs one box to represent those, and one would be spin up and one would be spin down. And that's how we would represent that. So to talk about this more, as we get more complicated systems where you have lots of electrons, we need to have a technique for how to talk about those electron configurations. And this is because most atoms are going to have multiple electrons. In the last chapter, we talked about single electron systems because they simplify our processes. But in most cases, you're going to have more than one electron. So we need to be able to talk about where are all those electrons located? How many electrons does our system have? So to do this, scientists create a concise list of all the electrons in an atom. And we call this list an electron configuration. So for example, for hydrogen, we write it like this. Hydrogen is 1s1. Some of this is a review from last chapter. Some of it one part's new though. So the 1 right here represents the number of the energy level. It's an n equals 1. The letter S here represents the orbital shape. That's L equals 0. The new part is this number in the top right. This represents how many electrons are in that orbital. So we'll start dealing with orbitals that can contain more than just more electrons. And so we need to count how many are in those. Now, there's a little bit more that goes into how we deal with all these different electron configurations. So to do this, we need to talk about something we call sublevel energy splitting. So the sublevels in each energy level of hydrogen all have the same energy. So when we talk about a 1 electron, 1 proton system, everything is the same. So if n equals 4, all the different L values have the same amount of energy. When two orbitals have the same energy, we say they are degenerate. I mentioned it here, we're going to use this terminology a few times. So when we talk about degenerate energy levels, it means when two energy levels are exactly the same. Once your atom has more than 1 electron, though, the sublevels split up so that not all sublevels have the same amount of energy. As a reminder, the sublevels are related to the L quantum number. So this means we'll get some changes there. So the lower value for the L, the less energy the sublevel has. So what this means is that we know there are 4 sublevels we said we had to learn the letter for, and those are going to appear in this order. So s orbitals are going to have lower energies than p orbitals, which will be lower than d orbitals, which will be lower than f orbitals, for the same principal energy level. So for example, this means that for n equals 3, you're going to have S and then P and then D and then F. But we're going to have to worry about how it intersects of, wait, what about when n is 3 for an s orbital, but for P, it has a value of 2. So we'll have to look into that some more. So this is this is the order when we only have one of them present. Okay. I got to pull something else up real quick. There we go. You don't see it on your screen. It was just to make sure I had something I wanted to do. So we've got one more. So what we need to do now is we look at what does it actually look like? How do we represent these multi-electron atoms once we start getting more than 2 electrons? Because we start having different sublevels. So this drawing is just a representation of a bunch of different energies. So on one axis, we're going to have energy. And this is how I'm going to draw it when I want to draw a bunch of electrons. So 1s starts at the bottom. Then as we set our principal energy level, we go up to 2s next. So n goes from 1 to 2. And you don't have any other 1 values. You can't have a 1p because when n is 1, L has to be 0. L can't be 1. Now when I got to 2 though, when n equals 2, my L could be 0 or my L could be 1. So then that's S and that's P. So I need to draw the 2s and the 2p. So for 2s, it's going to be lower, so 2p is going to go up a little higher. And we'll get 3 values for 2p. As a reminder, we have the 3 different placements that we can put electrons because it has 3 different m sub L values. You may remember from those pictures we looked at when you had those dumbbell shapes for the p orbitals, there were 3 different orientations that made a p orbital. Therefore, we need 3 different boxes. And in each of these boxes, we can fit 2 electrons. 1 spin up and 1 spin down. Now we've got some more energy levels. We'll have 3s next. And then we'll have 3p. But before we get to 3d, we're actually going to have 4s next. And then right after that, we're going to end up with 3d, which has 5 boxes. And then we'll end up with 4p. And then we'll have 5s. And then way up here, we'll have 4D. Now, this keeps going, and we're going to look at how to know the exact order in a number of slides later. You don't have to have that memorized yet. But do know that we are going to look at how did I know to put 3D where I did? Why did 4S come first? Another note I want to make. The left to right difference here doesn't mean anything. This x-axis doesn't have a label. The only reason we do the left to right change is so that it becomes possible to fit everything in an easy to see way. So we put all the P's on top of each other, all the D's and all the S's. But the part that matters is just the height. the energy difference. My 2s should be below my 2p. And so what this looks like, and we're going to look at different atoms and how they work, but if you might imagine an atom that had, let's say, 7 electrons, it'll end up looking something like this. And I'm only going to draw the orbitals that have energies in them. So if it had 7 electrons, I'd put 1 here, 2, 3, 4, 5, 6, 7. Now, what you may notice here is it may not be obvious. Wait, why did you put them from lowest to highest? And wait, why is it that they're all facing up? And why didn't they get paired together? In our next video, we're going to look at some different filling rules to help us understand where we put our electrons and in what order they occupy each orbital.